Okay, I'm going to do an example of a problem from Calc 1 that you may see, but a lot of folks don't know what to do with. So let's say the question was something like this. I've got x squared times the square root of x minus 4 dx. And I want to integrate this thing. Well, in Calc 1, I don't know any techniques that'll allow me to do this. No, but this is actually a Calc 1 question. It's in our Calc 1 book. So my argument here, if that had just been a square root of x, then I would just multiply these and this would be a piece of cake, but it isn't. So we would start by saying, let's let u equal x minus 4, and then du is obviously 1 dx. But here's where the problem lies. So now do I write this as x squared square root of u d, I don't even know, big question mark. What do you think about that statement right there? Are you happy with it?
No, there's two variables in it.
Yeah, it's an absolute impossibility. And by the way, a lot of people do their integrations this way. The moment you have two variables showing up in your integral, doesn't matter what you write next. It's not only absolutely in every conceivable way incorrect. I mean, you're going to have dogs sleeping with cats. I mean, it's craziness. You know,
Professor, can't you set up the x equal to u plus 4?
You beat me to the punch. That's exactly what you're going to do.
Sorry.
If u equals x plus or x minus 4, doesn't that mean that x equals u plus 4? And doesn't that mean that dx will still be 1 times du? But what that does, that gives us now an integral. I'm going to write it as u to the 1/2. So what I would do now is multiply out, distribute, and now I have actually a fairly simple integral. A lot of folks, when they see this, they call this the quote unquote reverse form of substitution. Actually, it's not. This is actually the main form of substitution. The main form of substitution, and we're going to do a lot of these when we get to what are called the miscellaneous substitutions a little later. The main form of substitution is actually to say, let x equal a function of something else, then dx is that chain rule factor, you know, probably du or whatever it is, and then substitute. In other words, this form of substitution is actually the dominant form. We learn u substitution first because it's the easiest and most practical to learn first, but it is not the one that is performed the most often. It's very common. So this version, so what we're going to do today, and by the way, this becomes a very easy problem, but it started off looking impossible. What we're going to do today is we're going to make substitutions where we replace x with a trig function. Again, that sounds insane at first, but there's only certain types of problems we're going to do this with. We're only going to do problems where the argument is a sum or difference of squares. Now, what I mean by sum of squares or difference of squares, my argument can be of the form x squared. I'll start with, sorry, let me start with, a squared minus x squared. It can be in the form a squared plus x squared, or it can be in the form x squared minus a squared. These are the only three ways I can have a sum or difference of squares. See, x squared plus a squared is the same as this, so I don't need to write it twice. These are the three forms of integrands that I'm actually looking at. Now, what's going to happen is I'm going to see these, any of three of these may be inside of a square root, maybe being raised to a power, maybe they show up in a denominator. But basically, I have arguments that involve one of these. What I want to do is choose the appropriate trig function to replace x with that would make it look something simpler. And here's what I mean. I want to replace x with either the sine of theta, the tangent of theta, or the secant of theta. How am I going to do that? Well, let's go and think of this. If I said 1 minus sine squared theta, I know that equals cos squared theta. If I said 1 plus tan squared theta, I know that equals secant squared theta. And if I said in the last one, secant squared theta minus 1, I know that equals tan squared theta. So each of these, this is constant minus trig function squared. This is trig function squared minus constant. This is constant plus trig function squared. These mirror these. But the a does not have to be a 1. Oh, you know, a could be 2 squared. Heck, a could be root 5 squared. You know, it doesn't matter what the value of a is, just a squared must be a positive number. So in each of these cases, I need to choose the appropriate x so that I could use one of these identities. Well, in the first one, I think it's pretty clear that I want to make x be the sine function. But what I need a squared minus x squared to work perfectly. So here I'm going to choose x equal a sine theta. And the reason I'm going to do that is that this will become, sorry, I'm going to write a little smaller. I'm going to run out of room otherwise. I'm going to choose x equal a sine theta. Then a squared minus x squared becomes a squared minus a squared sine theta. And if I factor out the a squared, that's 1 minus sine squared theta. And that's just a squared cos squared theta. Ah, okay. So if I have an integrand that looks like this, and I make this substitution, then this term here becomes that. And my hope is that that will make the entire problem easier as a result. So in the second one, I'm going to choose x to be a tan theta. By the way, the a is important because then it allows me to factor it out. And in the third case, I'm going to choose x to be a secant theta.
And then at the end of the problem, don't you have to go back and
yes, you
resubstitute?
Yes, you do. But it turns out that, I don't want to say that's trivial, but it won't be a deal breaker. Okay, I got to do a little bit of work, but I'm going to show you the route back. I'm going to show you the path to get the stuff. And you're absolutely correct. I'm doing an entire integral with a different variable. Oh, so at some point I need to go backwards. Well, how will I go backwards? Well, I will use that statement right there to go backwards. I will be able to figure out how to go back. It actually is not going to be complicated at all. And you're going to like this because it's going to take a problem we can't do as stated. We're going to change the problem through the appropriate substitution, do that problem, and then at some point change it back. So I'm going to do one of each type just to get you. Let's see, I'm going to erase this. This technique. Now remember, in math, we are the people that brought you, the formula that does this is called the formula that does this formula, right? And probably the single most important formula in all of algebra, the most commonly used formula, even through calculus, is the one where I give you a point and I give you a slope and you want to find the equation of the line. That formula is used not from just through algebra. It's used algebra through differential equations more than any calculus formula is used. You guys remember what that's called? The one where you have a point and you have a slope. It's called the
Point slope
formula. 3,000 years old, and that's the best we could come up with, the point slope formula. The formula that does this is called the formula that does this formula. The rule for taking derivatives of products is called the product rule. Yeah, I said math people are not creative in any way. So this way of integrating using trig functions as my substitution, is called trig substitution because we couldn't think of anything more clever, we should come up with really cool.
Why would you want to make it more complicated? Why not?
No, I laugh because you guys remember in Calc 1, when you learned how to do estimations using trapezoids, you called it the trapezoid rule. You're okay with that. But the one that involves actually parabolas is called Simpson's rule. And of course, everyone says, what the heck is a Simpson? No, that's actually named after someone. So in math, we don't like formulas and theorems that are named after people because we don't know what they are then. The farther you go in math, they tend to be named after people. So trig substitution, let's start with something relatively gnarly. Let's do, I have the integral of 1 over x times the square root of 36 minus x squared dx. Now you're looking at that going, gosh, that looks a lot like a formula that I know. It isn't, but what formula does that look a lot like? Anybody?
The derivative of the inverse trig functions.
Which one? Very specifically. It looks a lot like one of them.
The 1 minus sine squared.
Sine.
Well, if I flip those over, that's inverse secant. If I remove the x, it looks like inverse sine. It turns out it's neither one. But it kind of looks like one of them, doesn't it? No, there is no formula for this one. But it is of the form a squared minus x squared. Therefore, there's only one substitution that I can make. And I'm going to say, let x equal, anybody want to try it? By the way, this is really, really critical when you look at these. I don't say this jokingly. You can't see 36. What must
It's
it be?
6 sine
A
theta.
squared.
Always.
So
And by the way, do you know that this is true in Calc 1 too? All the way through, especially when you were doing, inverse trig and stuff in Calc 1. When you see a sum or difference of squares and things like that, don't see 36, see 6 squared. There is no 36 in the answer, but there will be a 6 in the answer because that's the thing that's going to show up. So I'm going to let x equal 6 sine theta. That's going to be my substitution. Now with that, what's my dx going to be? Like I said, this is kind of backwards from what you're used to. So the dx will be 6
cosine
cos theta d theta. And I do need the d theta because that's my instruction. I can't have a dx on one side and not a du on the other, because then I'd have an integral without an instruction. And that would,
wouldn't you want to make it let a equal? Because now you have x.
No, a is 6. That my a.
Okay.
Yeah. This is why I say identify what the a is first, and then that's going to show up. Now, what will happen is we're going to now manipulate this. So this is now equal to 6 sine theta, the square root of 36 minus 36 sine squared theta, 6 cos theta, and I'll now integrate it with respect to theta. Now, I took an integral that I don't know how to do, and I just made something absolutely god-awful looking. Well, but I can manipulate and perhaps simplify this greatly. There is absolutely no manipulation that could take place on this guy. If there was, I would have done it. So let's clean this up. Won't that be 36 times 1 minus sine squared inside there? So that means that now I have, by the way, if you want to go ahead and cancel the 6s, there's nothing wrong with that. So now on top, I have a cos theta. On the bottom, I have sine theta. But won't that just be then cos squared theta? So on the bottom, I have the square root of 36 cos squared theta.
So we can take the square root, I see.
Oh, I don't know about you guys, but I'm kind of liking the direction this is going. You see what's happening here? Cosine's now canceled. What am I left with? I'm only left with this. That's crazy. Now, I'm left with 1 over sine, which is the same as what? What's the reciprocal? Cosecant, which is probably our least favorite function. But I have an antiderivative formula for this. I don't have one for this. Oh my goodness. So here's the point. Through the appropriate substitution, I took something evil and scary, did some basic manipulation, and now I have a very, very simple integral, which I absolutely can integrate in one step. Now, if you don't remember this, by the way, and I don't say this jokingly, you should have that sheet of formulas next to you at all times during the class and when you're doing homework, so that you can always be refamiliarizing yourself with the Calc 1 formulas. So at some point, you don't need to look at them anymore.
Professor, not to be pedantic, but you also have the 1/6 up front in front of the integral.
I'm sorry, I couldn't say it again.
Oh, not to be pedantic, but there's also the 1/6 in front of the integral.
Did I lose?
Correct.
Oh, thank you, Fat Tom. No. That's part of the answer. So yeah, thank you. I don't want to lose that. Yeah, because then we get to the end and go, why isn't this working? It's off by a factor of 6. All right, so I get 1/6 natural log cosecant minus cotangent. That's one of those. By the way, we're done with the calculus. The calculus is over. But somebody pointed out, the antiderivative of a function of x really ought to be a function of x. So now the question, how do I get back? Go back to the statement here. If x equals 6 sine theta, doesn't that mean that sine theta equals x over 6? Everybody okay with that statement right there?
Yeah, and then you take the inverse of it.
No, easier than that.
Oh,
Draw me a picture where the sine of theta is x over 6. think SOHCAHTOA, very SOHCAHTOA. Don't think XY plane. I just want the right triangle, not the right, how about the correct triangle.
Y divided by,
So that would be the X. That would be the 6. Do you agree? In this picture is the sine of theta X over 6.
yes.
So what would this side be?
Y. Hold on. Square root of x squared plus 6 squared.
That's the hypotenuse.
Hold
So
on.
36 plus
Adjacent.
36 plus x squared.
hypotenuse 36
Minus x squared.
minus x squared. Right, this squared, this squared. Now, by the way, see that side of square root of 36 minus x squared? Huh, do you think it's a coincidence that that was part of my integrand? No. That's a good thing, actually, that it shows up. Now, if this statement is true, then this picture and this statement are saying the exact same thing. Okay, if I said, what's the value of x? You'd say, in my picture, the sine of theta is x over 6, so x is 6 sine theta. Now, why do I want that? Because in this picture, all I got to do is find what's the cosecant of theta, what's the cotan of theta, and then I'm done.
So
Now, this is a trick you guys learned in trig. You did it in pre-calc, and hopefully you did in calc 1 when you were deriving all of your inverse trig functions. So move this up a little bit. So my answer now is 1/6 natural log of what? Well, let's see. If the sine is this over this, isn't the
6 over
cosecant
x.
this over this? If tangent is this over this, then cotan is this over this. Does everybody agree with that? Now, that is the answer. Can I probably make this a little cleaner? What do you think? I want to make it just a slight.
Yes.
So why don't I do like this? That probably makes more sense, right? Whoa, that answer is gnarly. That answer is scary. And I really don't even want to take its derivative, by the way, but that's the answer. We took a problem that was unanswerable using any technique known to any human being, except for this one. This is the only way to get the answer to this problem. But when I did the appropriate substitution, the integral that I ended up evaluating, yeah, I know we don't like cosecants, but it was a single expression. There was no calculus technique to perform here. It's just antiderivative of cosecant. What you're going to find with trig substitutions in general is they will generally whittle down to some simple integral involving trig, and then I just integrate that. Then I'm going to go back to the original substitution, draw the appropriate picture, and then work backwards. So I want to remind you of something that you did a long time ago, perhaps, just to remember the point of the picture. Because I love the picture because it's so simple. Okay, you're in a baby trig class, and I say something like this. All right, the sine of theta is, 3/4, and theta's in the first quadrant. I want you to find the other 5 trig functions. You guys remember doing stuff like that? The other 5, well, do I need my calculator? No, actually, whatever you do, don't use your calculator. Because I want the answers. I don't want approximations of the answers. There's no time that you approximate an answer before you answer the question. So how do I do this? Draw a picture so that the sine of theta is 3/4. Is that picture accurate?
Yes.
Sine of theta? So then what's this side here?
5.
It'd be 4 squared minus 3 squared,
Just kidding.
7. Do you agree with that? Hopefully everybody agrees with that because that's correct. So again, there's a little rust here, I'm sure. So I drew a picture where the sine of theta is 3/4. That means the missing side would be √7. That's just Pythagorean theorem. Now, what's the cosine of theta in my picture? Well, that'd be √7/4. What's the tangent of theta in my picture? Well, that'd be 3/7, and so on. This is stuff hopefully you did in trig and or pre-calculus. It's a very, very simple way of filling in the blanks. I had to tell you what quadrant you're in, because if I was in a different quadrant, that could affect the plus or minuses. But this notion here is fairly simple. We're doing the exact same thing here. We just happen to have a variable. Okay, so let's try another one of these bad boys.
And professor, it's always the same if you have like an a squared minus x squared, you have to substitute x with a times sine theta.
Yes, the form, because depending
Those
on
are
it, is
the
it
rules.
is it a squared minus x squared? Is it a squared plus x squared? Is it x squared minus a squared? Those are three different forms. So that's what I showed you earlier. That determines. So let's do another one. Let's do,
I have a quick question. Are you
Sure.
allowed to build your own square? So if you had say 1 minus x, could you then multiply it by 1 plus x over 1 plus x to build the square?
Yeah, but actually, I don't know that that's the route you would want to take. You're going to take this route pretty much only when you have sums and differences of squares. If I had something that wasn't a sum or difference of square, there might be an easier way, hence second part of today's lecture. But there may be an easier way. But if I have a sum or difference of squares as the argument, especially if it's under a root or something, there really is no other way for the most part. So let's try another one. Let's do, how about 1 over x, 1 over x times, let's say 16 plus x squared. Now, there is more than one way to do this problem that we're going to find down the road, but I'm not interested in the other ways we might learn. I want to do this as a trig substitution because there's no u substitution that I could do here. You say, well, if I choose that as my u, isn't 2x the chain rule factor? It is, but this x is in the denominator, so that's of no use. So let's try this. Now, in this case, is it going to be sine, tangent, or secant that I'm going after?
Tangent.
Tangent, because then I'd have the case, think of it as like 1 plus tan squared-ish thing. So I have a 16, I'm going to see this as 4 squared. Okay. Now in the last problem, we had a 1/6 in there. We didn't have a 1/36, did we? Remember that? So oh yeah, I had that's where it showed up. So I'm going to let x equal 4 tan theta. Then that means that dx is 4 secant squared theta d theta. And if x is 4 tan theta, doesn't that also mean that tan theta is x over 4? I don't need this until the end. This will be the triangle that I draw at the end. It will be the triangle that makes this statement true. And that's how I'm going to be able to substitute back in the end. Okay. So in this case here, if I make this substitution, this will become, right, that's 4 tan theta. This would be 16 plus 16 tan squared theta. 4 secant squared. Okay, now let's clean this up. If I have 16 plus 16 tan squared, that's the same as 16 times 1 plus tan squared. But that's the same as 16 times secant squared. Ah. Can I do this? Boom, boom. Boom, boom. Is that legal? So what are we left with? We're left with that and that. Now, what's the reciprocal of the tangent function? Anybody?
Cotangent.
Cotangent function. Now you, oh God, another one. Well, cotangent theta is a lot friendlier than cosecant, by the way. And once again, evil, relatively simple. Again, this is why it's good to know the antiderivatives. The antiderivative of the cotangent, how fast are we? Can anybody tell me this one? Whether you have a sheet in front of you,
Log of sine.
What was the question?
that's called buying time. Log of what?
Natural log of sine.
Yeah, and we do put the absolute value, and the reason we put the absolute value is the sine function isn't always positive, is it? So I do actually have to have the absolute value because sine is going to be negative exactly half the time. But that's not terrible. I mean, I know what terrible is, and that's not it. Okay. So now we're done with the calculus. The calculus is finished. I just need to rewrite the problem using x's. So now I'm going to draw the triangle that goes with that statement. Now, that's where
Do we
theta.
have to draw the triangle?
Well, the answer will be the easiest to find if I draw the triangle. Let's put it that way. I mean,
Okay.
this is not one you want to do in your head, because if I do this in my head, I might get something in the wrong place. Trust me, this is of all the things you're going to do the rest of the semester, drawing the correct triangle is definitely at the bottom end of difficulty. But
In an exam,
the wrong
in a-
functions.
In an exam, would you want us to draw the triangle for grades, or we can do it like somewhere else?
Well, you probably want to do it within the problem. Like in the last problem, for example, my answer had a cosecant and a cotangent in it. I mean, do you know what the cosecant and the cotangent of something is without any reference? That would be kind of tricky. So I'm going to do this because it's easy. Now, what goes here?
X squared plus 16.
So 4 squared
root.
plus x squared, or 16 plus x squared under a root. Hey, what do you know? I had a 16 plus x squared in the problem. Now, the only thing that would make me suspicious that I was doing it wrong, I have a 16 plus x squared in the problem. If I had a 16 minus x squared, or an x squared minus 16 in my triangle, that would make me suspicious because it would be impossible. That's not possible. I will have this show up somewhere. Now, the sign is what? The sign is this over this. So I want this over this. In the absolute value, because that x can be negative, by the way. Okay, now what? We're done. That's it. Oh, well, that was cool. See, here's the thing. If this statement is true, I'm not sure I'm going to see that from this statement. That's why I'm going to draw the triangle. I just don't want to take a chance on messing something up, on having not everything be what it is. Now, is it possible in theory? Is it possible that this quantity here, assuming I didn't mess anything up there, is it possible this quantity here could actually be further simplified? Is it possible? Not today.
Yes.
Not this one. Yeah, but the rule of thumb is always the same. If you see an obvious simplification, take it. If you don't, walk away. Because if my answer is correct, but it could be simplified tremendously, all I have is an unfinished answer. An unfinished answer is not a wrong answer. Okay, I give you directions to my house, but your printer, there was a second page with one more line, and you printed them. I am that person, not like the commercial that says if you printed directions to get here, you're in the right place. I always print directions, by the way.
Okay, so we wouldn't be. Oh, sorry, Professor.
No, you printed directions, but you left the last line off here. So you got to my street. You just didn't get to my house, and you're walking around going, I'm hopelessly lost. No, I'm waving at you. No, I'm over here. In other words, you made it almost to the end. You just didn't finish. Okay, there's a small deduction there. You didn't finish. You're not wrong. You just didn't finish. But if you take a simplification that's not there, you went right at the stop sign when you should have went left. And now you have an answer that's completely wrong because you did extra work because you weren't sure. So I say, if you're not sure, leave it alone. If you are sure you can keep going, then keep going. Nobody's going to turn in the answer. And the answer is 8/4. I actually had somebody do this recently, and the answer was 2 minus 2. And that's what they wrote as their final answer on a calculus. The answer was 2 minus 2. Wouldn't you just say 0 at that point? It didn't dawn on them that it was 0. I don't know. They weren't wrong. They just weren't quite done. So if you're not sure, by the way, I can manipulate this all day using properties of logs. I don't think it's possible to improve upon it. So I'm just going to wave at it and walk away. Now, somebody had a question.
Actually, you answered it with your
okay.
explanation.
Yeah. Never confuse being unfinished with being incorrect. Incorrect means what you have is not going to work. It's not equal to the right answer. Something went wrong along the way. Being unfinished just means, for example, here's a perfect example. You wrote this and you walked away. Is this correct? Yes. Is it the final answer? No. So have you done anything wrong if you wrote this? No, but you're not done. You're not done until you write this. So if you stopped here, which by the way, people will do, they just, they went on to the next thing, they just completely blanked out. They forgot that they could keep going. You didn't say anything wrong. You just didn't finish the problem. And you still did it mostly right. So I say never confuse the two. Okay.
Professor, should we wait regarding quiz questions till after the?
Yeah, hold off. I'll give you a chance. We have just too much to go. Okay, hold on. Are you talking about the next quiz or the last quiz or the current quiz?
The one that was just graded.
Okay.
Quiz.
Okay, well, have you peeked at the key?
I did. We can talk after. I don't want to.
All right. Okay. All right. Whoops, sorry. I don't want to use, I'm going to use X's. Sorry, I can't read my own writing here. Let's do, where are we here? Here we go. X squared minus 9. Okay. Now again, if that had just been an X instead of an X squared, this would look like inverse secant, but it isn't, and I can't do anything about that. I can move constant multiples in and out of an integral. I can't move variables in and out of an integral. So this one here, again, the only way this can be attacked is with the trig substitution. Now, my argument is x squared minus 3 squared. So which function now will be involved in the substitution?
Secant.
So let x equal 3
secant.
Secant theta. If I get this part incorrect, then everything else I do will basically I'd be doing a different problem. So let's suppose hypothetically, when you were looking at this, you're just totally blanking out and you were seeing it as 9 minus x squared. Is that possible? Yeah. And so you said 3 sine theta. Well, from that point on, you're answering a different question. Now, you might be performing wonderful calculus, but you're answering a completely different question. If that's 9 minus x squared, the final answer is quite different. It is not the same thing. Can't commute a subtraction. So be really careful right here. Now, here's the funny thing about these problems. The rest of the problem now is self-navigating. Every single human being doing this problem should have exactly the same things at the same steps because it's kind of automatic now. You're on autopilot. That doesn't mean it's easy. That means you don't have to choose for the most part. 3 secant theta, tan theta, there we go. And then right away, I'm going to write secant theta is x over 3, because I'm going to come back to that, but not now. I'm not going to draw my triangle till the end just because it takes too much space right now. I don't know how much space I'm going to need. So we'll go to here. So 3 secant theta, and I'm squaring it. So that'll be 9 secant squared theta. 3 secant squared, 3 secant theta, and I'm squaring it. Squeakant theta. There we go. And then my chain rule factor, 3 secant theta, tan theta, and then all integrated with respect to theta. Theta is not a value. It does not show up in the quotient. That's actually very bad mathematics. People do that, but it's not correct. So 9 times secant squared theta minus 1. What is secant squared theta minus 1?
Tangent.
Tangent squared theta.
Tangent squared.
It's under the square root. Beautiful. By the way, it didn't have to be under the square root, but because it's under the square root, I'm going to take its square, or excuse me, its square root at some point. So I'm not going to cancel anything yet. I have too many things going on. So this one I'm going to wait to cancel just because I've got too many functions. So on top, I've got 3 secant theta tan theta. On the bottom, I have 9 secant squared theta. This is square root, so this will be 3 tan theta. Are we all cool with that? So far, so good? Now let's cancel like crazy people. All right. What does that leave me with?
1/9 cosine theta.
Yeah, 1/9 cos theta. And I'm pretty sure we know what to do with this one. Finally, something that's not, icky. So this will be 1/9 times the sine of theta. I am now finished with my calculus. But I'm not finished with the problem. So cosine is this over this, so secant is this over this. That's the easiest way to remember. So what is this length here?
Square root of x squared minus 9.
Good. And by the way, x squared minus 9, is that a good thing? Yeah, that's a really good thing. Can you tell me what the final answer to the question is?
1/9 sine of square root of x squared minus 9.
So, well, careful.
Oh, sorry.
Sine of theta? Want to be this over this?
Yeah.
So how about square root of x squared minus 9
Yeah.
x
Over 9.
times a ninth? So why don't I just go like that?
My bad.
Now, can I check this answer? Yeah, I can check it through differentiation. I'm not excited to check it. There's a lot going on there, right? There's quotient rule, there's chain rule, there's a lot going on. But if I take the derivative of this, I'm going to get back that integrand. But the calculus that we performed, I had to take a derivative of this to get my chain rule factor. That's the first calculus step. Then everything else was algebra until I got to here, and now I integrated. I think it's safe to say the derivative of this giving me this, and the antiderivative give me this. If that's the only calculus I had to perform, then this was pretty harmless. And this did not involve a lot of pain and suffering. Okay. And the fact is, I got an answer. Now, again, what seems totally backward is that I would take something algebraic and purposely change it to trig. What crazy person came up with this? But that by doing so, it made my answer much easier to find. So in other words, this is an extremely powerful technique. Okay, so what you're going to do in a problem of this nature is there has to be a sum or difference of squares. I can't have exponents other than 2. If this were x cubed, this is not trig substitution because there are no trig identities involving cubes, only squares. Okay. Now, someone said earlier, well, what about conjugating to make it a trig identity? Is that legal? Absolutely, that's legal. But it turns out there may be an easier path. If I don't have a sum or difference of squares, it's quite likely there's an easier way to get the answer. And that's kind of what we're going to do next is what ifs. Okay, so before I move on from this, because the next thing we're going to do is very different from this. Does anybody have a question on the trig substitution in general? Okay, I'm going to do one evil one in a moment, though, because we have really evil today. Yes.
Are the questions? I mean, they all look similar process. Are they all this way? Is there any variations, or is it just like that?
Well, of course, every version of this question, I could put more or less exponents. I could put stuff in the numerator. This doesn't have to be a square root. Heck, it could be to the 5/2 power. But the one thing you will see, and by the way, I'm glad you asked this. When I'm doing sums and differences of squares or sums and differences of squares raised to various powers, the powers will only be integer exponents or halves. And that's critical. There were no cube roots here. Why? Because when I did my trig identity, I have a 9 tan squared under a square root, which means I can evaluate it. What if I had 9 tan squared under a cube root? There's nothing I can do with that. Okay, so that's why you're only going to see exponents or roots, square roots, I'm sorry, exponents or square roots. So I could raise something to the 3/2 power, to the 5/2 power, 1/2 power, but you're not going to see cube root or 4th root or 5th root. You're never going to see that problem because this won't help. And that's important. Now, when you say variations, I could tweak this question a million different ways. But as long as it's x squared minus a squared, my substitution is still going to be the secant. If I change it to 9 minus x squared, now it's going to be the sine. If I change it to x squared plus 9, now it's going to be the tangent. And that's probably the most important part for you is to identify which substitution am I going to make. And there's no ambiguity, by the way. It's actually automatic. You just got to be mindful of what you're looking at. So there's only 3 forms again: a squared minus x squared, a squared plus x squared, and x squared minus a squared. Those are the only 3. Now, a squared plus x squared and x squared plus a squared are the exact same thing. That's why we don't have a 4th form, because sums are commutative. Now, I want to do one evil problem because there's some manipulation that will take place in some of the problems that you do. There's no way around it. And the manipulation is manipulation involving logarithms. Now, we know how to do antiderivatives that come up with logarithm answers. That's really not a big deal. But the algebra of logarithms and the manipulation, that troubles a lot of people, especially when there's a lot of simplifying or a lot of manipulation. It's kind of scary at times. So here's what we want to do. We want to find a general formula for the following. We want to find a general formula for anything of the form. Okay. I would like to find an antiderivative formula for this. And if you look in any calculus book, where that usually will have, maybe on the cover of the book, it'll have all the antiderivative formulas. Believe it or not, more often than not, this is the first one listed. Yet this isn't a formula you've ever seen or ever done. So why is it listed first? I don't know. But I know I have at least 10 different calculus books where that's the first antiderivative formula listed, yet you've never done this or seen this. So it's a little confusing. I want to come up with a general answer to this. You know, I'm not worried about what a is. See, what if this was 7 minus x squared? That just means a is square root of 7. I'm going to see a square root of 7 in my answer. I don't worry about the value of a. It's just going to show up. But this one here is going to require a lot of manipulation at the end. So which substitution am I going to make here?
Sine.
So let x equal a sine theta. Then dx is a cos theta d theta. All right, that was easy enough. And so this becomes a squared minus a squared sine squared theta. And on the top, I have a cos theta, and it's all dethated. Dethated, I guess, that's past tense of theta. So that's a squared times 1 minus sine squared, which would just be a squared cos squared. Great. So I have a cos on the top. I have a squared cos squared on the bottom. That means I'm going to have a 1 over a times what? Cos on top, cos squared on the bottom.
1 over
You'll be left with
sine.
1 over a cosine theta.
So what's 1 over cosine theta?
It's a
Secant theta.
secant.
Secant theta. There is no formula for the reciprocal of any trig function, so I need to just write it like that. Oh, well, that's a piece of cake. I know that one. In fact, I know the antiderivative of all of the individual trig functions. That doesn't trouble me. This is going to be 1 over a times the natural log of the secant theta plus the tan theta. Okay. As we say in my family, piece of cake. Okay. So going back to here, so sine theta is x over a. So I need a picture. X, a, so that would be a squared minus x squared under the root. Okay. So now my final answer. Oh, okay. I'm going to replace the secant of theta and the tangent of theta with whatever comes out of that statement right there. Okay. So now I'm going to bring that all the way over to here. I'm going to get 1 over a times the natural log of. Now, what is the secant? Well, let's see. Cosine is this over this. So secant is this over this. Tangent, this over this. All right, everybody with me? Everything I said is true and correct. Is that the best, most useful version of the answer, do you suppose?
You can combine them.
I'm sorry, say, I couldn't tell what you said.
You could do a plus x divided by the square root of a squared.
Oh, okay, so squash them together. Okay, I like that. All right. So a plus x over a squared minus x squared. Okay, great. Is this the best, most useful final version of this? Well, it turns out the answer is not quite. And here's this. We would be quite happy to walk away from this. But quite frankly, I don't even like the fact that I have a quotient, let alone a root and all these things. So off to the side, I'm going to do a little bit of algebra. When you derived the antiderivative of the cosecant, you had logs and you had icky stuff that hopefully in your class, you actually did a bunch of manipulation. It wasn't fun, but you got a way simpler answer. Off to the side, I would like to know can I simplify this? Actually, you can. How the heck can I simplify this? Because isn't a squared minus x squared the difference of squares? How do you factor a difference of squares? Wouldn't that be a plus x, a minus x? Well, it's under the root. Okay. Can I simplify this further? Absolutely. Why?
Because the top is a square root of the thing
Oh.
times the square root of the thing.
So now the top is this, and the bottom is this. You with me so far? Whoops, sorry. The bottom is this. I have a root over a root. Could I go a step further?
Multiply it by the,
No, not multiply. No, that would take me back to where I was. Can I do this? Is that true? By the way, this is correct. Is that true?
Yeah.
Yes.
No, I don't know.
No, I don't think so.
Well, okay, let me back up a step then.
Because then
Is
that would be
this-
the square root of the whole thing. Yeah.
Is that true? Is the quotient of roots the root of the quotient?
Yes.
Yes.
Oh.
Yeah, that is true. So therefore, why would I write it as 1/2 power? Because I'm putting it back into the log. Okay. I'm gonna keep going. Why would I do such a crazy?
So it's a 2 over a.
So 1/2a.
Oh, sorry, 1 over 2a. Yeah.
Oh my goosh. Now look what we've gotten ourselves into, folks. Look at the quotient now. There's no roots. There's no exponents. I don't know about you, but I think that is easier to work with than anything else I wrote down. And this is the final published version of this that you will always see. But it required some serious simplification. This is a correct mathematical statement. This is preferable because it's, I'm gonna put the plus C, it's easier to work with. It's way easier to work with, not even close. So it turns out, by the way, it's pretty much only with logarithms. When you have a logarithmic answer, if you don't see it, leave it alone. I think everybody saw from here to here. Okay. But the fact is I was able to do more, and then I was able to go from here to here, which is even better because there's no roots, there's no exponents. If you see an obvious simplification, you take it. If you don't, walk away. Okay, because you haven't said anything incorrect. But if I made an error anywhere along the way, this would be a wrong answer. It would give me the wrong numbers when I evaluate it. And that's the only thing we don't want to take a chance with. So this is the one evil problem we're doing today. And there was nothing about the calculus that was difficult. It was the manipulation of a logarithm, which is a very, very common thing for this type of problem, because so many of your answers are going to involve logarithms. Well, why would so many of my answers involve logarithms? Because of the 6 trig functions. So 4 of the 6 trig functions have antiderivatives that are logarithms, right? Secant, tangent, cosecant, and cotangent, their antiderivatives are all logs. So you see logarithmic answers with trig a lot more often than none. Okay, so now we're going to go to the next thing. We're ready. So this is trig sub, and the nice thing about trig sub, there's no ambiguity. It's obvious when you're going to use it, because first of all, you didn't see anything else that worked. I mean, you know, if you have a u sub, I'm going to give you a really simple one. Am I going to do a trig sub on this one? I can. Am I going to do a trig sub?
Well, wouldn't we use the formula, or no, wait.
If that's my u, isn't that a multiple of du on the top? So that's just a simple u sub. This, because I've got the chain rule factor sitting right there, this would be a simple u sub. Now, what if I had that? Oh, now I might do trig sub. Or what if I have, you know, that? Oh, now I might do trig sub. If I see an obvious, you know, oh, that's just a u sub. Oh, that's just an antiderivative formula. Here's another fun one. This one, I love asking this question. All right, well, absolutely, I can do a trig substitution on this. Is there anybody lazy here? I can do a trig substitution on this. Or simply write the answer, because that's an antiderivative formula we know from Calc 1. That's inverse tan. Now, if I did the trig substitution, just so you know, I would have gotten inverse tan as my final answer. And then you'd go, oh my gosh, I think, but it's okay. So if you see an obvious out because you already know how to do it, you take it. But I don't know any other way of doing it. I have sums and differences of squares in the integrand. I'm going to do a trig sub. If you see another way of doing it that's easier, you take that way. All right, so let me ask you a simple question. I would like to take something of the form, let's say 3 over x plus 1, and I want to add it to 6 over x minus 2. And I want to write this as one quotient. Okay? I want to write this as one quotient. What would you do? Well, first of all, do you agree that that would be the denominator?
So it'd be 3x minus 6 plus.
Yeah, so if you were in a baby algebra class, you'd probably do something like this. And therefore, what would your new numerator be? You said, so it'd be 3 times x minus 2 plus 6 times x plus 1. And now you have 9x.
Just
You
9x.
have 9x. And your bottom is x plus 1, x minus 2. And by the way, a rule of thumb is you actually would prefer to leave your denominator factored than not. It's correct to multiply it out, but there's no advantage gained. Okay, great. So you got that answer, and now you're totally happy with that answer. Great. And now Mr. Brown comes along and says, oh, by the way,
We need to integrate
I
that.
need you to integrate this. And you say, I don't know any antiderivative formulas for this, because you don't. And you go, oh, shoot. And I erased all the stuff I wrote down. Well, of course, now it's when you just replay the lecture and watch the video. So here's my question to you. How do I go backwards and recapture those original quotients? I would really rather write this in terms of the original quotients that I had, because
Long division.
no, because the numerator's of a smaller degree. That, by the way, that's a great thought. Hold that thought, because that will come up. No, it turns out,
Partial fraction?
it's something you learned in pre-calc, and all of you hopefully forgot completely to make this worthwhile. You're going to do this.
Oh yeah, that thing.
It's called, anybody know what that stands for?
PDF.
Good. Partial, oh, I'm sorry.
Portable document format.
I'm dyslexic on this one. Partial fraction decomposition. You go, oh yeah, we spent maybe 30 minutes, maybe an hour, heck, maybe 90 minutes of your life in a pre-calc class doing these problems. I can guarantee you there was absolutely no application whatsoever, because there isn't any at the time. And when you ask your instructor, why are you doing this?
Yeah,
Your
use it in
instructor-
Calc too.
If your instructor wasn't a calculus teacher, they probably couldn't even tell you why. You need this because now you're in Calc 2 and you use this actually quite often. The problem is we learned this a long time ago and we never use it for anything. So it's really unusual when I have a student who actually remembers how to do it. So we're starting from scratch, folks. I do not assume any prior knowledge in terms of recollection, but when we get through, I want you all to be experts, because even if you never learned it well, we're going to go through it enough now. Partial fractions decomposition basically means I'm going to take something where my denominator is a product and I'm going to split it up. That's the decomposition part. There's only 2 types of factors. There are linear factors and there are what are called irreducible quadratics. I'll get to that one later. Okay, so I want to solve this problem right here. Well, the easiest way to do it is to multiply through by the common denominator, or which is the same thing as saying put this over one denominator. It's the same thing. So if I put this over one denominator, now that they have the same denominators, I'm going to equate the numerators. So basically, I'm solving the following problem. Okay, everybody cool with that? Now, turns out There will be a solution, and the solution is unique. There's exactly two ways to come up with the solution. I'm going to show you the textbook approach, and then I'm going to show you the right way. In other words, there is a fast way 100% of the time, and there's a long, slow, drawn-out way that is what you see in the textbooks. So the textbooks approach is what's called equating coefficients. It's absolutely correct. No, there's nothing wrong with it. And says, first thing I'm going to do is distribute ax minus 2a plus bx plus b. Now I'm going to equate coefficients. So I have a plus bx plus negative 2a plus b. And I'm going to set that equal to 9x. Oops. That means I'm going to get two equations and two variables, my variables being a and b. What are my two equations? Well, think of this as 9x plus 0 if you want. That means that the a plus b must equal 9. And that means the negative 2a plus b must equal 0. And now I'm just going to use some baby algebra to solve this. And what I get as an answer is the answer. And that's absolutely correct. But it's the absolute longest, most drawn out way of doing something. And here's the drawback. I have two quotients. What if I had 3? What if I had 4? What if I have 5, which by the way is not unusual in any math or physics example? That means you're solving that many equations and that many variables. Once you get past 2, you can't do it this way. The only way you can possibly do it is using a matrix. We're in Calc 2. How many of you would consider yourselves experts in matrix algebra? I don't even have to look at the screen to know no one's raising their hand. In other words, if I have a situation of 5 variables and 5 unknowns, I'll give you a month and you'll come back and still have no idea what. No, you don't want to use a matrix to solve this. I teach matrix theory. You don't want to use a matrix to solve this. You want this to be simple. You want this to be a slam dunk. Equating coefficients is absolutely correct. It's the way that's always taught. I would hope you also learned the shortcut. Equating coefficients is correct because I'm going to get 2 equations and 2 unknowns. But there's an easier way to get my 2 equations and 2 unknowns. And that is to pre-select the values of x that I want to actually use. I get to choose. I'm going to pick 2 values of x that are convenient for me. You know what 2 values I'm going to choose?
2 and negative 1.
I'm going to choose 2 and negative 1. Because when I choose negative 1, then the left side of the equation is negative 9. The right side of the equation, well, that would be 0. That would be negative 3 times a. And this implies, that's what that symbol is, an implication symbol. If this is true, then this is true. Okay, there's my a. Now I'm going to choose x equal 2. I'm going to choose things that make my quantity 0. By the way, if you choose any 2 real numbers, it doesn't matter what those real numbers are. You will get 2 equations and 2 unknowns, and you can solve it. I'm picking the only 2 numbers that my 2 equations and 2 unknowns only have 1 unknown in each equation because the other unknown is going to be 0. It's easy. So if x is 2, then that's 0. So I'd have 18 on the left equals 3b on the right, which means that b is 6. Now I've recaptured the original problem. So that means going back, let me erase this. That means that this is 3 over x plus 1 plus 6 over x minus 2. Now, before you go any further, it would be very wise. Manipulate that. Do I get this back again? Is it possible I make an arithmetic error in here? Well, of course it's possible. You know, losing a sign is possible. So I don't want to just automatically assume that I did it correctly. I always want to check my work. Now we can go back to the original problem. The original problem, and the whole point of learning partial fractions decomposition generally is for integration. That's why in pre-calc they couldn't tell you why you're doing it, because you didn't know what an integral was. Okay, so that means this is equal to the integral of this. And that's simply 3 natural log x plus 1 plus 6 natural log x minus 2. And now I'm done. Okay, there's no other math I could use to get me from here to here. I have to go from here to here to here. So partial fractions decomposition, our favorite partial fractions decomposition problems are ones that involve only linear factors, because that's the easiest one. Algebraically, in every conceivable way, and it does not matter how many factors you have, because having a lot of factors does not make something harder, strangely enough. I know it seems like it should be harder. Nope. Because if I'm using this approach, if I have lots of factors, I can still do one at a time, even if it's, lots. Okay, let's do another one of these. And in this case, I don't even care about the integral. I just want to do the partial fractions decomposition. Excuse me. So let's do the breakdown, all of this, of the worst problems that you'll be asked are ones where it's not already factored, but most calculus books will give you things in a factored form, or at worst, it'll be a quadratic that you can easily factor. You're not going to see a fourth or fifth degree polynomial in the denominator that you got to factor all the way down. You're just not going to see that, because that's a branch of mathematics that we're not looking at. I'm not asking your ability to factor high degree polynomials. No. I'm saying if I have something of this form, and by the way, I could have 3, 4, 5, doesn't matter how many factors I have on the bottom. How do I attack this? Well, the first thing I do is I break it up, and the breakup's usually the same. Something like this. And that's step one. My goal is to find the values of A and B to make this true. And the nice thing is there can only be one value of each. There are an infinite number of possible A's and B's, but there's only one pair that will actually work. So the next thing I'm going to do is basically multiply through by the common denominator. And I can say X equals. Before, what I did was I put them over a common denominator and then I equated numerators. Let's just go right to that step. So what does X plus 22 equal then?
A times X plus 4 plus B times X minus 2.
Beautiful. Now from this point on, because I have linear factors, I should have the final answer really in under a minute. Even if I have the TV on, and I'm distracted, because the algebra required to finish this is actually quite trivial. Is it possible A and B could be nasty fractions? Yeah.
Sure.
If I just made up a random problem, A and B are almost certainly going to be fractions. The only time they're not going to be fractions is if it's reverse engineered. Yeah, A and B can be fractions. That's not an issue. So folks will say, oh, I got a fraction. I must have done it wrong. Really? If I put any coefficient on here, both A and B would be fractions. If I change this 22 to almost any other real number, they'd be fractions. I just happen to use friendlier numbers. So I'm going to pick two values. I'm going to start with X equal 2, because that'll make this term 0. But don't forget to plug it into the left side. So the left side would be 24, and the right side would be 6 times A. And that gives me the result A equals 4. Now I will choose X equal -4. That will give me 18 on the left, that's 0, and that will give me -6b on the right, and that leads to b equals -3. Therefore, the answer to the question is 4 over x minus 2 minus 3 over x plus 4. And if I had to integrate, obviously the integration would be trivial. Okay? Everybody cool with this so far? All right, now let's go to the next layer. The next layer, because I'm giving you linear factors, obviously factors are not always linear. Now there are some very important mathematical concepts that lead into this, all of them involving something called the fundamental theorem of algebra, which is something in a perfect world your pre-calculus class would have spent a lot of time on. That's the things like rational root theorems, knowing if I have a higher degree polynomial, knowing which numbers to use, and then using synthetic division to whittle it down, and stuff of that nature. But really it comes down to this: all polynomials. Okay, I'm going to give you the sort of the roots so you understand why, and then you don't have to waste time on things that aren't important or don't exist. I have a polynomial, an nth degree polynomial. I'm going to write it in this form here. A0 plus A1x plus A2x squared plus all the way up to an x to the n. I know you usually write it in descending order. It really doesn't matter, but you'll find in this class, because of the nature of things, you usually write it in reverse. It doesn't matter. I can absolutely say, if I factor out the an, this is an times x minus r1, x minus r2, dot, 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 x minus r to the n, or r sub n. I've just factored in the n factors. And you notice whatever that coefficient is, if this was 25 x to the n, that I'm factoring out the 25, and now it's the coefficient of 1. This is an absolute. Yeah, I don't have to prove this. I have R factors. That's the R's are called the roots. Okay, some of you, you've had math classes where they called the R the roots, or they're sometimes called the zeros, which is confusing. It's the values that make it equal to 0. So in the last problem, we had a denominator of x minus 2 and x plus 4. So the roots were 2 and negative 4. Those were the values that made it 0. This is an absolute. An nth degree polynomial can be factored into the n linear factors. Some of the factors may be repeated and some of the factors may be complex. Okay, so what if these two guys here were actually x squared, plus 4? That would mean I have x plus 2i and x minus 2i. Those are imaginary roots. And that is absolutely correct. You can have imaginary numbers in the factorization, but imaginary numbers in my factorization isn't very useful to me because they're not real numbers and we're only doing real valued calculus. We're not doing any calculus where I have potential imaginary numbers showing up. Therefore, I'm not going to look at it in this form. I'm going to look at it in this form. So the x squared plus 4 is what's called an irreducible quadratic. Or another way of saying it, it's a quadratic with no real roots. And that is critical information because if my roots are imaginary or worse, complex like 2 plus 3i, that's not going to help me. That doesn't help me in the partial fractions decomposition. It certainly doesn't help me in the integration. Okay. So with that said, absolutely all of these can be factored into this, but some of these I need to go backwards. An irreducible quadratic, again, has no real roots. Well, what about if I have quadratics? Do I have to go back to the cubes? No. A cube must have at least one real root. It does? Yes. If I thought of the graph of a cube, y equal x cubed looks like that. I can have cubes go like this. I can have cubes go like this. Where it crosses the x-axis is the root, by the way. I can have cubes do anything you want. A cube must cross the x-axis no matter what. It's impossible.
Is it because it's odd?
Because of the degree being odd, exactly. As x grows without bound, it's going up. As x goes negative, it's going down. A cube has to cross the x-axis no matter what. A cube can cross the x-axis as many as 3 times, but it has to cross at least once. If my cube only crosses once, that means there's one real root. That means there's one linear factor and one irreducible quadratic. If it crosses multiple times, that means there's multiple roots. That's it. That's it. That's all we need to know to justify why we never need anything bigger than an x squared. I never need an x cubed in my denominator because there's got to be at least one real root. Now, we tend to concentrate on happy roots. In the first example, I didn't have any roots that were fractional. I didn't have any roots that were square roots. That's okay. All of those are legit. All of those are legal. We tend to stay away from because the algebra gets too nasty. Now, in baby algebra, when you had a polynomial you couldn't factor, you called it prime. And I hate to say you were lied to. You'll find a great deal of the mathematics you've learned in your life was, I don't like to say you were lied to as much as saying the truth was sort of withheld. You've never had a no solution. There's nothing you've ever done as a no solution. It might be no real solution, which is for all practical purposes essentially the same thing. But the further you go in math, the complex solutions become just as important as the real solutions. So when you were told a polynomial couldn't be factored, baby algebra, and this is important for what we're about to do. We know this. We have no, that's obvious, duh. Now you're in remedial algebra and you have this. So of course, what did you say in baby algebra? Well, that's prime. That can't be factored, duh.
It's just the square root of 7.
Yeah, I'm pretty sure. I'm pretty sure that's the factorization. So what we called prime is when I didn't have integers in the factorization. In other words, that's not prime. That's not even like prime. That's prime. What makes it? But I can factor this. You're right. So technically, that's not even prime. If we're going to call something prime, let's call something prime that only has imaginary roots. But technically, I just factored it, so it's not prime. There's actually no such thing as prime. There are things that cannot be factored with integer factors, or there are things that have no real roots. So if we're going to call it prime, let's call this one prime, when technically I just factored it anyway. We called this one prime, that's a lie. So my point being is really are no restrictions when I start not worrying about imaginary numbers. We will do nothing with imaginary numbers here. Therefore, I'm never going to factor it to here and then continue. I'm going to go back to this step here. So when we are doing the partial fractions breakdown, and I have a denominator that looks like a sum of squares, I'm not going to try to factor it because the factors would involve imaginary numbers. I'm going to leave that as one of my factors. So let's do an example of exactly that. Let's suppose I have something of the following form. I have 14x minus 4 over, let's see, what did I want to do? Over x minus 2 times x squared plus 4. And ultimately, by the way, I want to integrate this. Now, someone mentioned long division before. Long division would only be necessary if the degree of the numerator were not smaller. But right now it's smaller, so it's great. If that x had a large power, then actually I would have to use long division. That's for another time. We'll probably look at that problem tomorrow because we're going to do more of these tomorrow. So
Wait, isn't
Monday.
Monday, you mean? Because
by the way, just you know, tomorrow always means next class.
yeah, you scared me, man.
In the 2 day a week, by the way, in the 2 day a week classes, I'm notorious for referring to tomorrow and yesterday. I'm like my little children. You know, when my daughter was little, she'd go, "Daddy, you remember yesterday when I was born?" You know, she used to use that one a lot. Well, the fact that she's saying this verbally, she probably wasn't born. But I'm notorious. When I say tomorrow, I mean next class. When I say yesterday, I mean last class.
My heart dropped.
That's how my brain works. No, I'm giving you the weekend off.
I mean,
Also-
I'm game to be tomorrow.
No,
Yeah.
I'm not.
Anyway, so we want to know, what do I do with this guy? So let's do the partial fractions breakdown. I'm going to walk you through what's necessary now. When you have, and again, that is called an irreducible quadratic because the only roots are imaginary numbers. So I'm not going to mess with it. I'm going to leave it alone. So I'm going to write this as a over x minus 2. The question is, what do I do with this guy? Well, here's the rule of thumb, and I just gave you a hint. When you have a rational function, that's a quotient of polynomials, you can never deal with any rational function in any capacity, derivatives, integrals, graphs, or anything. You can never deal with the rational function unless the numerator is of a smaller degree than the denominator. See, if I put an x in the numerator here, that means I could manipulate it and make it smaller. Okay, so what numerator do I want? I want the biggest possible numerator I can have that's still a smaller degree, but this is second degree. Therefore, I want a linear numerator. So some of you may remember this. Now, it doesn't mean I have either one of these. My final answer might have a 3, or my final answer might be 2x, or my final answer might have both an x and a constant. I don't know until I do it, but I allow for the possibility of either one of these. Okay, so when you have an irreducible quadratic as a denominator, you do the partial fractions with a linear numerator. When you have a linear denominator, then you do it with a constant numerator because you need it to be of degree 1 less. Okay, that's it. That's an absolute unchanging rule. If I mess that up, let's say I only put a constant on top here, I might not be able to solve this. Okay, I might run into an impossible situation. So now when I multiply through, 14x minus 4 will equal a times x squared plus 4 plus bx plus c times x minus 2. Now it looks a little bit busier. And by the way, if I multiply out and I equate coefficients and do all that, that's all legal. But now I'm going to have 3 equations and 3 unknowns, and I'm not excited to do that one. Now, I have to pick 3 different values for x, and I think it's pretty obvious there's only one value that's going to cause an entire term to be 0, but I can be very strategic. Okay, so what's a good starting point? Anybody?
X equals 2.
Okay, let's start with x equal 2. On the left side, I will have 28 minus 4, or 24. If x is 2, that entire thing is wiped out. X is 2. So 2 squared plus 4 is 8. So I have 8a, which gives me a equals 3. Great. But now what do I do? You can pick any real number you want.
Well,
There's one really good choice about right now.
0.
0.
0.
Then I can get rid of the b. Let's pick x equals 0. Again, for that reason right there. Now, if x is 0, then left side is -4 equals. But don't I have an a, b, and a c? Not anymore.
Well, you can substitute the a.
You already know the value of a. Okay, so if x is 0, then right here I have a 4. I'm going to write times 3 so we remember where it came from. Or better yet, actually, let me write it as 3 times 4. We already know that answer. Now what do I have here? If x is 0, I have -2. Does everyone see that? If x is 0, that's -2 times c. I think that's pretty easy. So this is what? -4 equals 12 minus 2c. So if I throw that over, that'd be -16 equals -2c. And that means that c is +8. Did I do that right? Let's see. Did I mess that? Let me see if I did. Make sure I didn't mess that up totally. So if x is 0, I have -4 on the left. I have -2c. And I have 12. I think that's correct. Okay. You with me so far? Everybody okay? Now, question is, now what? What do I do now?
Now you can just pick any simple x equals 1, for example.
Exactly. Perfect. I said we had to pick 3 values. So now I say, what value should I choose? The answer is yes, because it doesn't matter now. Pick something small. I'm going to pick 3/2. I'm going to pick pi. I'm going to pick something small and easy. Why? Because you've already got a and c. You only have to find b. Oh, okay. So I would pick probably +1. I just, by the way, would +3 be a good choice? Because I'd have a 3 here, but then I'd have to do more calculations. I'd probably go with 1. So if x is 1, then what's my left side?
10.
10. My right side is x is 1. So that's 5. So that's 3 times 5. X is 1. So that's b plus 8. X is 1. So times -1. I don't want to do too many steps in my head. I don't want to get lost here. So we all cool with that? I have 10 equals 15 minus b minus 8. So that's 10 equals 15 minus b minus 8. So let's see, if I throw the b over and I throw the 10 over, I think that gives us b equals, hold on, what is it? Let's see, if I throw the b over, then I have 7, so -3?
-4 is what I got.
I think -3. 15 plus 3 minus 8. Yeah, I think b is -3. Okay, we good now? Hopefully. So, because I'm going to run out of room, I'm going to rewrite this now. Where was our, here it is. So I've got 3 over x minus 2 plus -3x plus 8 over x squared plus 4. Wow. But you notice the algebra was still pretty low level. This was not complicated. It wasn't short and sweet because I had to solve for 3 values. Can I integrate each of these? I don't know. I think the first one's pretty trivial. Is this something we can do? Better yet, here's a better question. Is this a Calc 1 problem or a Calc 2 problem in terms of the integration itself?
I see a trig sub in the bottom,
Yeah. And
Yes,
but I also see the
you see
multiple
u
in
sub
the
t
north.
possibly.
Yeah.
In other words, trig sub will always work, but do you see something that we could do without? By the way, I love trig sub, but I have to roll up my sleeves and take a little time. if I can get the answer before a trig sub, that means I can get the answer sooner and easier. How about if we look at the numerator? I'm going to erase all this because it's in the way. How about if we look at that numerator? First one's trivial. Let's go with 3x plus 8 over x squared plus 4. What if first thing I do? This is the duh. Sometimes we don't think of this. Why don't I do that? See, we're looking at 3x plus 8. We're looking at 3x plus 8.
In the integral in the top, you drop the negative sign on the 3.
Yeah, it's a -3.
Oh, thank
Yeah.
you. That matters. Okay. Yes. Later on, when it's not working though, why isn't this working? Negative. Okay. Now, if I break it up like this, then treat these independently because they're going to have completely different antiderivatives. Here's a u sub. If that's u, then my du is 2x. Oh, okay. So this one is just -3/2 times 2x over x squared plus 4. That's just a straight up, that's going to be a natural log. How about if I rewrite this one as 8 times 1 over x squared plus 2 squared? What does that look like?
An inverse function.
Inverse.
Let me look at the sheet.
The most common of the inverse functions, inverse tan.
Inverse tan.
The mistake a lot of us will make, we got to here and we're happy, but we're looking at this as an entire numerator I must deal with. No. Break it up and go, oh, one of them's going to be a log, the other is going to be an inverse tan. You will find that combination, that's a major point of next day's lecture, by the way. A major commonality is to see inverse tans and logs in the same answer to the same question. They kind of go hand in hand, because when I have an inverse tan type of problem and I change my numerator to a linear numerator, it usually becomes a natural log kind of problem. So the final thing here, I'm going to rewrite this way. I've got 3 over x minus 2 minus 3/2 times 2x over x squared plus 4 plus 8 times 1 over x squared. You can write 2 squared or 4. We can now answer each of these directly. It is totally legal to do u sub. But remember yesterday I said if you see it right in front of you, if it's sitting right there, well, let's do the first one. That's 3 log x minus 2. If that's my u, that's my du. So that is log x squared plus 4. I'm going to hold off for a moment. Generally, when you integrate to get a logarithm, you always put absolute value because of the possibility that the argument is negative. Do I have to put absolute value on this one?
No, because it's squared.
It's not wrong to put absolute value. Do I have to on this one? Your argument is a sum of squares. Do I need absolute value on this one?
No, it's always positive.
Always positive. Is it wrong to put absolute value? No, but it's not necessary. That'd be like saying the absolute value, the answer to the question is the absolute value of 5. Wouldn't that just be 5? A lot of times we don't. Oh yeah, that's right. I have the absolute value of a strictly positive quantity. It is legal to do this. When you're doing a substitution, you said the answer is the log of the absolute value of u. No, you do need it there because until you substitute your argument in, you don't know if it can be positive or negative. Oh, okay. And then the last one, we said inverse tan. That's 2 squared. So it's 1/2 x. Remember, it shows up there. Times 1/2 times 8. Wow, that is some serious gnarliness. This is the final answer. Now let me ask you a question. Are you happy with this answer? Can we manipulate it? The answer is probably yes. Should we manipulate it? You're hoping the answer is no. What if I could do any manipulation whatsoever? What would it involve?
Combine
Just
the
pulling out the
logs.
fraction.
Well, the
Combine.
logs. Is
Oh,
there
yeah.
any advantage to combining these logs, by the way?
So when you're calculating, you only have to do it once.
Yeah, you're right. But I have to mess with the exponents and then quotients, and I've got to apply a few log rules. And you're right. But is there necessarily an advantage in this case? The rule of thumb I like to use when it comes to logarithms, if I've got coefficients, I usually don't like combining them unless they have the same coefficient. Because if you want to do this, it is totally legal. You would say, okay, this is the log of x minus 2 raised to the third power. And this would be, if you want, you can write plus or minus, the log of x squared plus 4 to the 3/2. Now I'm going to write this as log of, x minus 2 to the third power over x squared plus 4 to the 3/2 because there was a minus. That's correct. I don't know, that kind of scares me. That's correct. I don't know that presented any advantage, or that I just made the problem really nasty. I'd probably just leave it in this case. Now, there is the one exception that I want to point out, because this will come up quite a few times over the next week or two. There is one time you should always combine logs. The final answer to the question is log, let's say 7 minus log 2. The final answer to the question is log 12 minus log 2. Which one should I manipulate? Which one should I leave alone?
The bottom one, because the 12 divided by 2 is less than.
Yeah, that's a no-brainer. Oh, because the difference of logs is the log of the quotient, infinitely preferable to this. But this one would be log of 7/2, and I really don't like logs of fractions. Again, if I'm using a calculator, I'm more likely to mess it up because now I got to do the parentheses. No, I'd probably leave this one alone. This one, absolutely, I do this because that's way, way simpler. Personally, I don't like logs of quotients. Okay, because you're just giving a numerical answer. Now, if I needed a decimal answer on my calculator, I would just do it from here, and I always remind people, and in my Calc 1 class, a lot of folks just, they took them a while to get the hang of this. In a math class, you always give the exact answer. That's the answer. Okay, that's it. I'm done. This is the best answer. Now I'm in physics, and this represents a distance. It represents maybe a volume. Maybe it represents a speed. I'm in chemistry. I need this many milliliters of solution. I'm going down to Home Depot later on today, and I need log 6 feet of wood. Pretty sure they're not going to have a marking on log 6. So in other words, if you're doing a measurement for a science class, your answer might be log 6, but at some point you might need to convert it to a decimal because you're going to use it to, might be a length or a volume or something else. Okay, in a math class, you're not doing lab science. So if the answer is log 6, the answer is log 6. That's fine. There's no time you ever have to convert that to a decimal. But like I said, if you were in a science class, you probably would want to convert that to a decimal because, again, that represents a measurement of something. That's all. Okay, everybody cool with that? All right, this is a good stopping point. There is more to do. There's exactly 3 types of problems, and I gave you 2 of them. I gave you the linear factors, and I now have introduced the irreducible quadratics. There is one more, and it is truly evil, and I have never seen it presented in a calculus or below text in a way that I am happy with. But in differential equations, it becomes one of the most common algebraic techniques, and you will learn a completely different way of doing this problem that you've never seen before. In other words, you're going to learn the right way to do it in DiffyQ. No, I'm going to teach you the right way to do it in Calc 2, but it won't be in any of your textbooks. Does anybody know what the third one is? It's the one we like the least. There's one more version of this question.
Log division.
Well, no, that's something aside that will create repeated factors. See, I just wrote it to a power. The worst problem that comes up is the one where you have repeated factors. Algebraically, it is the worst. Trying to find your coefficients, by far the hardest. And the textbook approach for repeated factors, it's almost impossible to do that. When I say the textbook approach, I mean the way that it's presented in every textbook that's ever been written, the way that's presented in almost every math class. If you have repeated factors, it's virtually impossible to solve the problem without using an advanced matrix. And you shouldn't have to use math you haven't learned. You go, but we learned it in baby algebra. Yeah, but not like this. We're going to do a problem next day. I'll keep it simple. We're going to do a simple partial fractions next day. I'll do an easy one. I don't even want it to be complicated. let's do a simple partial fractions next day. You know, we can do 3x minus 4 over x minus, I don't know, 3 to the 10th power. If you do the traditional approach, I'll give you a month, but you have to stop. You would take you page upon page upon page, hours and hours and hours and hours and hours and hours and hours. I'm going to show you how to do this problem from beginning to end in about a minute. This would be the scariest problem you could ever run across in any lower division math class if you didn't know the technique I'm going to show you, which is not in any of the calculus books. A repeated factor is the gnarliest kind of problem to work with from an algebra, not from a calculus point of view. And that's why I kept that separate. So next day, we're gonna look at that. And someone asked about, well, long division, when does that come in? We'll also look at a problem where I may have to do long division before I start the problem. But that's actually a fairly simple notion. Okay, so we will continue on the partial fractions next day with just a couple of more types of problems and then go on to our next technique. Now we'll go ahead and pause. Hold on, pause.